Hi, in this video we are going to talk about linked list data structures, so let's get started. What are linked lists? Linked lists are composed of nodes and references or pointers pointing from one node to the other. Of course, the last reference is pointing to a null, and basically it's very important because this is how we are able to detect that the last node is pointing to a null. So in this situation, the first node is the node 1. It is pointing to the node 2, it is pointing to the node 3, it is pointing to the node 4, and the node 4 is the last node because it is pointing to a null. So basically it's very important because this is how we are going to implement linked lists, that we are going to iterate through until the next node is a null. So basically this is how we are able to detect that it's going to be the last node in our linked list. So what about a single node? A single node contains two important items. First, the data itself. It can be an integer, it can be a double, or it can be a custom object, whatever. And it contains a reference or a pointer pointing to the next node in the linked list. Of course, if it is the last node, it's going to point to a null. So if we would like to implement the node class, whatever in Java or Python or C++, we have to create a node class, and basically in the node class we can have everything we want, but two important features we have to include: the data we would like to store and the reference to the next node. It's going to be a node, of course. So each node is composed of a data and a reference to the next node in the sequence. It is a simple and very common data structure. Linked lists can be used to implement several other common data types such as stacks or queues. It's very important that simple linked lists by themselves do not allow random access to the data. We have been talking about arrays, and we have pointed out that the most important feature for the array is the random access. So we are able to get the items according to the indices. In this case, we do not have any indices at all, so we cannot use these indices. So the get item according to the index cannot be implemented. And many basic operations, such as obtaining the last node of the list, or finding a node that contains a given data, or locating the place where a new node should be inserted, require sequential scanning of most or all of the list elements. So basically, we have to iterate through and visit all the nodes in the linked lists in order to find an item, for example, or remove an item, or something like this. Of course, if we are manipulating the first item of the linked list, unlike arrays, it's going to be very fast. So what are the advantages for linked lists? Linked lists are dynamic data structures. We have been considering arrays, and we have come to the conclusion that arrays are not that dynamic. We have to specify the size of the array at compile time, and we have to specify that what kind of data we would like to store at compile time. So they are not dynamic at all. Linked list can allocate the needed memory in runtime, so they are dynamic in this sense. It is very efficient if we want to manipulate the first elements. It's going to take order 1, so constant time complexity, to insert an item at the beginning or remove an item from the beginning. We have been discussing arrays, and we came to the conclusion that it has an order n, so linear time complexity, to insert items at the beginning or remove items from the beginning of the array. And what's very important, basically it is true for arrays, that it's very easy to implement the linked list. Linked list can store items with different sizes. It's very important. An array assumes every element to be exactly the same. So that's why I say, although I don't want to repeat myself over and over again, that linked lists are much more dynamic data structures than arrays. And it is easier for a linked list to grow organically. An array size needs to be known ahead of time or recreated when it needs to grow, and this reconstruction of the array takes ortho and linear time complexity. Here, for linked lists, we are able to add a new node. Basically, we just have to update the references, the pointers, and it can be done in ortho 1, so constant time complexity. What about the disadvantages for linked lists? It wastes memory because of the references. As we have discussed, every node contains a reference to the next node. It's going to be the pointer basically, and of course, it's going to consume lots of memory. So, it's going to waste memory because of the references. Nodes in a linked list must be read in order from the beginning, as linked lists have sequential access. Array items can be reached via the indices in constant time complexity, but here for linked lists, we are not able to use random access, so we have to use sequential access instead. Difficulties arise in linked lists when it comes to reverse traversing. So single linked lists are extremely difficult to navigate backwards, and the solution is the doubly linked lists, when basically we store a reference to the next node and we store a reference to the previous node. It is easier to read, but memory is wasted in allocating space for a back pointer. It's very important then for arrays, we don't have to store a reference to the next item or the previous item. So in this aspect, arrays are very memory friendly. For a linked list, we have to use at least one pointer pointing to the next node. But when it comes to double linked list, we have to use double references, one reference to the next node and one reference to the previous node. But it's going to be easier to read the data and make any other operations. So that's all about the advantages and disadvantages of linked lists. In the next video, we are going to talk about the operations concerning linked lists. Thanks for watching. Hi. In this video, we are going to talk about linked list related operations. First, we are going to consider insertion. So inserting items at the beginning of the linked list is very simple. We just have to update the references, and it can be done in ortho 1, so constant time complexity. So for example, we have the linked list and we would like to insert at the start the item 10. Of course, this is the first item, so we are going to insert it, and it's going to point to a null. Okay, then we would like to insert 4. Of course, we just have to insert the 4 and set the pointer point to the next node, which is the 10 in this case. What about if we would like to insert -5 at the beginning? We just have to insert it, and we have to set the pointer pointing from the -5 to the next node, which is the 4 in this case. So if we inserting items at the beginning, we just have to set this pointer pointing to the next node, which is in this situation is the 4. So this operation is very fast, and this is why we like linked lists basically. As you may recall, for arrays, if we would like to insert at the beginning of the array, so the index 0, then we have to reconstruct the array. So instead of the ortho 1 time complexity that we have seen here for linked lists, for arrays it is ortho n, so linear time complexity. It's very important to see that we like arrays because of the random access and because we can insert items at the end of the list very fast, ortho 1 time complexity. We like linked lists because we can insert items at the beginning, not at the end, at the beginning, very fast, ortho 1 time complexity. Okay, so inserting items at the end of the linked list is not that simple because we have to traverse the whole linked list to find the last node. And how do we find the last node? Because we know the last node is pointing to a null. So this is why this null is very important as far as linked lists are concerned. And of course we have to update the references when we get there. Okay, updating the references is going to take order 1, so constant time complexity, but the overall complexity will be order n, so linear time complexity, because first we have to iterate through all the list. So we have to consider every item in the linked list. And okay, what about arrays? Inserting items at the end of the array is very fast. Inserting items at the end of the linked list is quite slow. So for example, we have this linked list with the 12, 4, 123, -7, 10 items, and we would like to insert 25 at the end of the linked list. It's very important that we can access only the root of the linked list. So here for linked lists, we are not able to make random access. We access the root of the node. What is the root of the node? It is the first node, which is the 12 in this case. So we consider it. So we have to get to the last node. So how do we know that that's the last node? That it's pointing to a null. Okay, so is it pointing to a null? No, it's pointing to 4. So let's hop to 4. Is it the last node? Is it pointing to a null? No, so we have to hop to the next node, which is the 123. Is it pointing to a null node? No, so it is not the last node. -7 is not the last node as well. But 10 is the last node because it's pointing to a null. So we just have to update the references. And instead of pointing to the null, this 10 is going to point to the item we would like to insert. So it's going to point to 25, and 25 is going to point to a null. So in this case, we have managed to make sure that this 25 will be the last item. Okay, it's very important that updating the references again takes constant time complexity, but first we have to traverse the list itself, and that what takes order n. So order 1 plus order n is equal to order n. Okay, so that's why inserting items at the end of the linked list takes order n linear time complexity, while on the other hand, inserting items at the beginning of the linked list takes order 1, so constant time complexity. Okay, so that's what we have been discussing. Inserting at the beginning is order 1, inserting at the end is order n, so linear time complexity. What about the remove? Removing item at the beginning of the linked list is always very fast. We don't have to search the item, we just have to update the references accordingly in order 1 constant time complexity. Okay, so we have the linked list with items 12, 4, 123, -7, 10, and 25. And we would like to remove the first item, basically the root of the linked list. We just have to remove it, and basically in Java, for example, we just have to set it to null. Okay, what about if we would like to remove the next item? In this case, the root node is the 4, so we're just going to get rid of it. Quite simple and fast operation. What if we would like to remove an item at a given point of the linked list? It's not that fast because first we have to search for the given item, which may take a lot of time if the item is at the end of the list. So that's why it's going to have an order n linear time complexity algorithm. And it's very important, although I don't want to repeat myself over and over again, that we are not able to use random access as we have seen for arrays, because here we can access the root node only, and with the help of the root node we are able to traverse all the linked list with the help of the next node pointers, but anyways, we can access the root node only. So we would like to remove the 10. Okay, first we have to search for it. We start at the root node, and on every iteration we pose the question that is it the item we would like to get rid of? So the 12 is equal to 10? No, so we keep going, we go to the next node. 4 is equal to 10? No, we keep going. Is it the item we would like to get rid of? No, we keep going. -7 is not equal to 10, so we keep going. But here we have managed to find the item we are looking for. So basically we just have to update the references. The previous node, So this -7 is going to point to the next node of the node 10, which is the 25 basically, and this is how we are able to get rid of the 10. We just have to update the references. First, we get rid of the 10, and the previous node, which is the -7, is going to point to the next node, which is the 25. So we get rid of the 10, and basically this is how we get rid of an item from a linked list. Okay, the time complexity will be linear, so ordo n, because we have to find the item first we would like to get rid of. Removing items from the beginning takes ordo 1 constant time complexity. Removing items at given positions is usually ordo n in the main, so linear time complexity. It may happen that, for example, the item we would like to get rid of is at the beginning of the list. Okay, then we are lucky. But in average, it's going to take ordo n divided by 2 time, and of course ordo n divided by 2 is equal to ordo n. This is how big ordo notation behaves. So basically that's all about linked lists. It's very important to see the difference between arrays and linked lists. Both of them have some advantages as well as disadvantages, and we have seen that we have to make sure that we use the proper data structure because it depends on what kind of application we would like to implement. If we would like to manipulate the beginning of a list, then we have to use linked lists because array list is going to operate slower. If we would like to have random access, then we have to use arrays on the other hand. So sometimes array lists are better, sometimes linked lists are better. In the next video, we are going to talk about the problems concerning linked lists, and we are going to talk a bit about doubly linked lists. Thanks for watching. Hi, in the previous video, we have been discussing linked lists operation, but there are some problems with linked lists. We can get from 4 to 25, for example, because we just have to hop to the next nodes. But the problem is that we cannot go from 25 to 4 because the references are in the opposite directions. So basically that's why doubly linked lists came to be. And of course the node class has 2 references in this case. One pointing to the next node as we have discussed in the previous examples, and another one pointing to the previous node. And basically why is it good? Okay, so we can get from everywhere to everywhere, but it is not so memory friendly because we have to store lots of references. For every node, we have to store a pointer to the next node and another pointer pointing to the previous node. And basically, why is it good? It's good to have a reference to the next node and the previous node because we are able to traverse the linked list in both directions, and sometimes it can prove to be very important. So basically for linked list, we have seen that okay, we store a reference pointing to the next node, but sometimes it can be very useful to have a reference to the previous node as well, and basically that's why doubly linked lists came to be when there is a forward edge and basically a backward edge to the previous vertex. So that's all about doubly linked lists. Thanks for watching. Hi, in this video we are going to talk about the main differences between linked lists and arrays. So let's get started. What's the difference between these data structures as far as the search operation is concerned? The search operation yields the same result for both data structures. So if we are looking for something, it's going to return the value if the given data structure contains this given value, or anyways, it's going to return null, for example. Array list search operation is pretty fast compared to linked list search operation because we can use random access for arrays. So the get item is going to be very fast because we can specify the index, which is going to yield ordo 1, so constant time complexity operation. On the other hand, linked lists has ordo n, so linear time complexity, as far as the performance is concerned, because we are not able to do random access for linked lists. So if we are looking for an item, we have to start at the root node. It's very important. I have mentioned it several times, but for linked lists, we are able to access the root node. So we have to iterate through all the list and basically have to check on every iteration whether this is the item we are looking for. And of course, in the main, it's going to take linear time complexity. So the conclusion is that ArrayList is better for this operation. You may pose the question that, okay, why? Because ArrayList maintains index-based system for its elements, as it uses array data structure implicitly, which makes it faster for searching an element in the list. So if we know the index of the item we are looking for, it's very important that it's true if we know the index of the item we are looking for. If we don't know the index, then we have to iterate through arrays list as well, and the operation is going to have ordo and linear time complexity. Searching for ArrayList is going to be very fast if we know the index of the item we are looking for. So linked list requires the traversal through all the items for searching an element, and that's why the search operation is going to take linear time complexity for linked lists. Okay, what about deletion? Linked list remove operation takes ordo 1 time if we remove items from the beginning of the list, and usually this is the case. This is why we like linked lists. On the other hand, for array lists, removing the first item, so if we want to remove items from the beginning, it's going to take ordo n, so linear time. And removing the last item takes ordo 1, so constant time. So it's very important to see the difference that for arrays, it's very fast to manipulate the last items, whether it is about removing or inserting an item, but manipulating the beginning of the list is going to take ordo and linear time. For linked lists, manipulating the first item is going to take ordo 1, constant time complexity, so very fast, while manipulating the end of the list is going to take linear time complexity. So for arrays, on average, we have to reconstruct the array when removing an item in the main. So for example, if we would like to remove items from the middle of the array, of course we have to reconstruct the array. So the conclusion is that linked list is better as far as the deletion operation is concerned. Okay, why? Because linked list basically operates with pointers. So the removal only requires changing the pointer location, which can be done very fast. For arrays, we have to shift all the items, and that's why it's not going to be as fast as for linked lists. What about the memory management? Arrays do not need any extra memory because we are not going to store references to the next node. Linked lists, on the other hand, do need extra memory because of the references or the pointers. So in this aspect, arrays are better, they are memory friendly, so we don't have to store extra pointers to the next node or the previous node for doubly linked lists and so on. So array lists are memory friendly, linked lists are not so memory friendly. So just to summarize again, what about the search for linked list? It's going to have ordo and time complexity. For arrays, if we know the index we are looking for, it's going to take ordo 1 constant time complexity. What about inserting items at the start, so the beginning of the list? For linked list, it's going to have ordo 1 time complexity. For arrays, it's going to have ordo n time complexity because of the shifts we have to make. What about inserting at the end of the list? For linked list, we have to iterate through the whole list. That's why it's going to have ordo and linear time complexity. For arrays, we are able to insert it in constant time complexity because of the random indexing. What about the memory management or the space we waste with the help of these data structures? For linked list, we have to store a reference to the next node as far as every node is concerned, so that's why the memory complexity will have ordo n, so linear memory complexity. For arrays, we are not going to store any extra data except for the data we would like to store, of course. That's why the waste space will be 0. So, according to this table, we can decide what data structure to use in a given application. It depends on what operations we would like to use frequently, whether we would like to insert at the end of the list or at the beginning of the list, whether we would like to search according to a given index, or we would like to search for an item where we do not know the index. So basically, according to this table, we are able to get the data structure best suited to the application we are going to implement. So that's all about the differences between lists. Thanks for watching.